Good morning, everyone, and thanks to the earlier presenters. It's been great so far. I wanted to talk today about an update on the open access extensions, the Polygon Operators, or OAXPOP for short. We have some new features coming in, but before I do that, I'm going to just give some background on what we've used these operators for historically, give an overview of what we've had as a baseline. And then I'll go into some new features, some new connectivity extraction features that we're adding, that we have been adding, and we are just literally tidying up right now. We'll be releasing finally after a couple of years of effort. And I'll show what it is in a step-by-step approach. I'll show the extracted result using both graph and node output structures. And then I'll get into a little hello world example using Python code and highlight a couple of potential applications that this new feature will bring. And the two that I'll highlight will be node highlighting and layout netlist creation, basically. And then I'll share just a couple of high-level pictures of some block-level extraction results. Okay, so first, again, the background on what we have had in OAXPOP for quite some time. Basically, OAXPOP was initially released, again, as an open access extension, and it basically provides high-speed polygon manipulation capabilities. So you can kind of see some images below, and obviously this is the bread and butter of EDA. We have the basic operations of AND, OR, XOR, and NOT of polygons to one polygon set to another. And then there are higher level operations that are kind of shown here, like, inside, outside, touching, butting, straddling, and so forth. This is a subset of what is available, but just kind of gives you an idea of what it is. It basically leverages the open source Boost Polygon library, which was actually contributed by Intel in 2008 and is available as an open standard there as a C++ library. OAXPOP takes that engine and plugs it in with the open access objects directly, such as OA shape, OA box, OA point array, and so forth. And we have used this library in conjunction with OA script very heavily across Intel in various business groups, and including many that I've been involved in directly. And I've given some SI2 presentations on those in the past at prior SI2 and DAC events. Just as again, a little bit more on the background on the timeline, we're about a decade into it now. We started, even though it was contributed, the engine was contributed by Intel in 2008. It wasn't until a few years later that we picked it up and made OAXPOP. And that was in 2011, so we're about a decade old now. And we've made several releases since then. There was a bit of a hiatus. We were stable and we haven't done anything for a while, and then we recently revived it and released a pure set of Polygon operations in December to handle some direction, relative direction-based operations for that core functionality. I won't be talking about those today, but there are some new features in there that just got released. But then there's been a separate thread, and like I said, it unfortunately has been a multi-year effort simply because of time, developer time, and focus. And we've refocused. I've drawn a line in the sand, and I'll be sending out a note to release, to get this released, and it takes about a month to approve that, and then we'll go ahead and next month we'll go ahead and release them, and people can start using them in a 2.0 version. So, all right, so let me explain what exactly it is that we're going to be releasing. So it turns out that Boost Polygon, it always had within its capability to do basically electrical extraction, basically connectivity extraction. We never exposed that because our primary focus, as I mentioned earlier, was on the Polygon operations, the Booleans and so forth. But there is a need for something like this, and I'll explain why in a minute. And so we looked at it, we said, let's go ahead and expose these features as well. And so what I'm showing here is one of the designs that was contributed to SI2 from NAND it's a very small logic cell. And I'm gonna, I wrote some code to basically extract the nets out of it, and on the lower left side is kind of like a YAML implementation, my own. This is not part of the standard. This is just my own idea of how we could create drive layers. These drive layers are needed to do connectivity extraction. Otherwise, you need to separate things like the source drain regions of the device and the gates and extract those differently. And so that YAML data file there is just to simplify the code and make it configurable for other technologies if we wanted to reuse this in other places. Yeah, so I think that's that. And then I guess at the bottom, just to draw your attention, the bottom of the table does define. So the top part is the derived layers. So for example, we take a diffusion, we give it an open access derived layer number, we give it an operator of AND. We say that formula is basically the layer 1 is active and the layer 2 is an implant, and that will result in extracting a source drain region, the diffusion itself, and then later on we extract a source drain region by taking a gate out of it, for example, and I'll show in the next slide. And then we define the connectivity buildup. So for example, in this case, poly is connected to contact, and it also is connected to end gate. I actually extracted that end gate shape as a separate layer. So it's basically the same thing as poly, but it was separated out, and so that's how that works. Okay, and then the source drain regions, and then metal 1 in this case. All right, so let me kind of do the build up step by step so you can see this. The engine will actually take any shape in any order. It doesn't matter. You don't have to put it in any particular way. You just keep feeding it shapes, and it will internally determine how to deal with those shapes later based on the connectivity stack. And so here, I'm just going to build it up bottom up, but it need not be in this order. And it will assign an index to it. And actually, these indexes are a little bit higher for some of these shapes because I did feed all these shapes in a different order than what's shown here. But just to kind of highlight, each of these shapes receives a number, and it's assigned to a layer. And then that layer is tucked away and reused when we go to extract later. Okay. So I'm only really going to be showing the layer numbers for one node on here. I mean, every single shape in this, whether it's going to be extracted as a net or not, is going to have a index assigned to it. All right. So then next are the contact shapes. Those also get numbers, and they get thrown into the extractor engine. And then finally, the single. In this case, I'm just looking at this particular net. Of course, all of the nets are extracted, but I'm going to be highlighting just this net as an example for this case here. That metal 1 is added, and then when you run the extractor and you say, okay, give me the result, then it associates all of those shapes as being connected to something that's sensible, basically a net. So this node says that based on the connectivity buildup I had previously defined, if I just select one of these shapes, it will provide a path to all of the other shapes that are electrically connected to it using an adjacency graph, through traversal. And then you can pick any one of these numbers that I showed you before, and it will take you, whether you're going up or down the stack, however many layers, it doesn't matter. It's not limited by, sometimes people have done things where they only support one layer up or one layer down. This is true extraction. It'll go through everything. So there's that. So you can actually navigate it by either a graph if you want to follow it through that way, or just say, hey, what give me the nodes, or here's a shape, what node is this shape a part of? And it will answer that question for you. Okay, so that's how it works. Let me give you a hello world, and I'm going to apologize ahead of time. Usually when we show hello world programs, you end up with about 1 or 2 lines of code. That is just not going to be the case with this. It's a little more complicated. I mean, I could have done it maybe in about 5 lines of code, but it would not have been as very interesting. So it is a little bit longer than you normally would see, but let me just walk through this for you. I use Python. These are available in Ruby as well, and of course the C++ under is there as well, and then Tickle. And we have stopped supporting Perl officially, but this does compile. So if somebody is sympathetic and wants to test Perl, then to some extent this should work as well with Perl. But okay, so let's go through the Python here. So the first step is to define our layers. So here in this example, I have Metal 1, VO1, and Metal 2, and I'm going to build up these this picture basically in the shapes down here. But I define Metal 1 as being a layer, and then because you can actually have more than one layer purpose pair associated with Metal 1, for example, you may have a Metal 1 drawing, a Metal 1 fill layer, or other layers that may be represented on different layer purpose pairs in open access, but electrically are the same layer. It is a little bit more verbose, and so you have to define the container, and then you can have, usually you just have one, but often you can have more than one. And so we add a layer purpose pair for shapes, associating it with this con layer, this connectivity layer. We do the same thing for VO1, the same thing for Metal 2. And in this case, I'm going to also assign a text layer purpose pair on Metal 2, saying that if you find a text label somewhere, then that text label would be part of the extracted result to associate a net name with the connected shapes. And then I create the engine, basically the extraction object. And so currently in this first release, we'll just support 90-degree angles just based on time to get something out there, 90-degree angle shapes. But there will be in a later release, connectivity extraction 45-degree or any angle. And based on the prior presentations I've given on OAX Pop, the data that was shared by the Boost Polygon library is that you're going to have a lot faster operations with a 45 versus any angle, and then even faster with if you limit it to 90 only, because you can make certain assumptions in the API. So that's what we're starting with, and I think that handles most of EDA anyway. Anyway, so we create the engine, and then we build up the connectivity. So we say that VO1 connects to Metal 1, and then VO1 connects to Metal 2. And now I have a path that goes from Metal 1 to Metal 2 because we go through that VO1. The next several lines aren't very interesting. I mean, they just basically describe these shapes in the upper right corner. And I give it the open access layer number and purpose number. And then, excuse me, in this case, we can read in OA shapes and OA occurrence shapes directly, in which case you don't need to provide this information, obviously. But since this is a hello world ground up, this is showing you that you can use a primitive OA object, like an OA box or OA point array, and you need not have any design even loaded. You can actually read a text file with these shapes. I mean, some of the prior presentations showed YAML files and data files that could have coordinates in them. I mean, you could read that, and you could read in a def file or whatever, and build up something without even opening an OA design if you wanted to. Or you can use the OA design approach too. But since this is hello world, I'm keeping this simple. And so I just, on the fly, synthesize several boxes and points for the, I'm actually synthesizing a text label here, A and B as shown. And then this is where the magic happens. So we then create a con graph object, which will take the engine object And at that point in time, it performs the extraction and presents you with a graph and says, okay, you can now see what you have inside, basically. And you know, here I just printed how many nodes that were found. So in this case, there were 2 nodes that were found total. And then I loop through the nodes from the graph. So again, in the graph, I can either go through it in graph mode where I say, you know, starting with this shape, let's follow it through. Or another way is just, you know, going about it by the nodes. And so that's what this one is doing here. And so I just wanted to show me what electrically connected islands of shapes has it found. And the first thing I do, and I can also, you know, there's a helper feature in there to calculate the node names on a node. Excuse me, calculate the net names on a node. And the reason why there may be more than one net name on a node is because, you know, you could have a short circuit, of course, whether it be something that was intended to short together or, you know, was a problem is something that you're going to have to find out, I guess, depending on how your program handles that. But you could have 0 or more, you know, net names based on text labels that were used for a given node. Okay, so there's that. And okay, so now, you know, for applications, so we use this again on the NAND gate library that was contributed to SI2. And there were probably about, I'm just doing this off the top of my head, there were probably about, I think maybe 100 or 200 logic cells in there. And we, you know, went ahead and ran this on all of them. And as you can see, there's several net nodes in each one of those cells. And so, and you know, interestingly enough, I dumped that output out into a YAML format for storage as a golden reference. I actually found a lot of problems in the original code in doing this, you know, debugging it. But now that it produced a result that's expected, that has been stored away in YAML on Git for the reasons that were mentioned in prior presentations. And we can, it's stored in a sorted and deterministic way that allows us to do further, you know, diffs later on as we change the code to confirm that, you know, the behavior has not changed basically from one code state to another. But this is showing a visualization of the various nets that were extracted, and you can see that it clearly is doing the right thing, basically. So then I did another one. I did this one just recently, just to show, you know, some of the other applications that could be done with this. And I have disclaimer: I haven't been involved directly with any kind of LVS for more than 10 years, and so, you know, this is not intended to be an optimal way to do LVS or whatever. This is my own invention, I guess you could say. That's just more of a theoretical to demonstrate what can be done. But I wrote about 335 lines of Python code total with comments and so and a little bit of error checking and other, you know, overhead. But basically, it reads in a YAML file very similar to what I shared before for the connectivity buildup. And then it defines the devices. So here I'm extracting an NMOS and PMOS device, and I, you know, I'm associating it by the N gate and P gate derived layers. And then I identify the terminals. I'm not doing the bulk. Obviously, the bulk would add some weird complexity. But yeah, I'm just going to do the terminals. And then I'll extract parameters to check. So the width and height and length of the device, which will be extracted as a height of an extracted box size, basically. So now that I look at that, I think I got that backwards. So anyway, so let's not worry about that. So that's funny. But in any case, you know, so I ran it through and basically produced this output. So again, now that I've just realized I got those backwards, that's kind of embarrassing. But basically, it takes the open access cell name, the terminals that were found, that were extracted and found, and it extracted the nets, and then it found the devices based on the derived layer, and went ahead and associated the gate and the source and drain nets with our terminals with the nets that were found, basically. So yeah, I mean, that was just kind of like a little fun thing, like I said, is to show you one potential application. I had shared this example previously, about a year or so ago, when we still were working on the code, but we did, once again, there was another NAND gate contribution for a larger block, 500 by 500 micron block with, let's see, it looks like there are about 144,000 nets, 50,000 instances, and there was a total of 3.7 million shapes. And it took about 1 minute and 40 seconds. I have not checked this recently. We'll have to, I would presume that it would be better, if anything, based on recent work. But it took about 1 minute to insert the shapes into the engine, and then about 37 seconds to extract after they were inserted. And I have a little, the breakdown of shapes if you want to look at that later on. But you can see that it was able to pull out, something sensible, basically. Okay, and so just to kind of wrap up and summarize, Open OAX POP already had very useful features that are available in the 1.x series of the release. We're now 10 years old. We are just about to release these features into the library for general use in next month, and these new features will definitely add value to OAX POP based applications. In particular, being able to navigate node and graph-based data structures to do things like net highlighting, layout, netlist creation. And I really wanted to do this for this presentation, but I ran out of time. But maybe do a shortest path, kind of algorithm where you can extract, decompose the layout into various individual shapes and then show that. So, but that'll have to be for some time in the future. And that concludes my presentation. If there's any questions.
James, just one question from me. Could OA partitions play a role in the calculations here?
Yeah, I think it probably could. It's been about a year or so since I've looked at OA partitions, but to be able to, I guess along the lines of load the data partially and then maybe open various threads and extract those regions independently and then bring it together. Is that what you're getting at? Something like that?
Yeah, just wondering if there was a fundamental limitation whether it would work together.
I think that's something we're going to have to test. That's a good question, really good question. That, in my opinion, would make a lot of sense. Yeah, I think that would be something that we need to test. I don't see any reason why it would be a problem. There is only one, at least currently, there's only one extraction engine. So you would have to have some way to, some kind of a mutex of some sort to basically, tell, if you're doing it multi-threaded, to say which one is putting things into that box that thing at a time, I guess. But yeah, I don't see any reason why you couldn't.
Yeah, I wonder if the fact that the graphs you're getting are cyclic, they're not nice directed cyclic graphs anymore, but it may not impinge.
Yeah, it should be fine. The graph is it's direct adjacency to begin with. Okay, so you should be fine there. But yeah, it should be. I don't see any reason why you couldn't. But it's a very good question, and definitely. I'm just happy to get this out the door right now, so I'm going to get it out. But I think that we should look at that.
Cool. Thank you.
Mm-hmm.